Hello. This week I want to show you how to implement a simple game for two opponents using JavaScript and the Minimax algorithm that you met in the lecture on game playing from last time. Link to that in the description below, by the way. The game I've chosen to implement is Connect 4, as it's a fairly simple one. I considered writing a chess playing program and even tried programming it for a few days, but it all proved too difficult. And since I have to keep the projects churning out, I had to put that particular project aside for a later date. Maybe you'll see my JavaScript chess player in future weeks. So, Connect 4. For those who aren't familiar, it's a game for two people, one playing the red discs, the other playing the yellow. They take turns to drop a disc of their colour in at the top of a column on a vertical board that is 7 columns wide and 6 rows tall. The discs drop down and the columns fill up from the base. One player wins when he manages to get 4 discs of his colour in a continuous straight row, vertically, horizontally, or diagonally as shown, hence the name. You'll also notice that, in fine programming fashion, the columns are numbered from 0 up to 6, rather than 1 to 7. I have chosen to implement a simple 2-level game tree. The first set of branches represent the 7 possible columns, and each of those branches has 7 possible comebacks from the human player. This secondary level is a minimizing level, i.e. the minimum score for each of the human's possible replies is copied up to the first level. The first level is a maximizing level, and the program will choose the column corresponding to the largest value at that level. If this were a chess-playing program, it would be necessary to copy the current board position at the top of the tree to each of the nodes in the first level, each of the 7 nodes in the middle of the slide in this case, and then the change corresponding to that branch will be made to the copied board. Then for the next level in the tree, each of those board positions will be copied again for more changes to be made. We can short-circuit part of this workload as we don't need to copy the current board down into the first level. No board is to be evaluated at that level. We need to copy the current board down 2 levels, and each of those boards is a straight copy with 2 extra discs dropped, a red, computer, one followed by a blue, human one. Given that there are 7 possible computer moves, each of which is followed by 7 possible human responses, the lowest level consists of 7 times 7 equals 49 board positions. By not populating the intermediate levels with copied board positions, we save having to make and store 7 copies. The hard part of the program is to score each board position. Here's one way of doing it, not necessarily the best way, but a relatively easy one to implement. You'll agree that a line of 2 discs the same colour, or more so 3 discs the same colour, are promising, but all that promise disappears if a disc of the opponent's colour is preventing it being extended to 4 discs. Here's my way of scoring the board, and I'll use the board position that you've just seen as the example. For each player, the algorithm considers the first empty space on each of the 7 columns. Of course, if a column is full, that column is skipped. For each non-full column, the algorithm asks, if I dropped a disc of a given colour onto that column, what will be the longest chain of that colour, horizontally, vertically or diagonally, extending from that disc that could still be turned into a line of 4 on some future move. Take this cell, for example, the one marked with a question mark. If I dropped a red disc into that column, the longest line of reds that would result would be 3, extending diagonally from lower right to upper left. Could this line be extended to a line of 4? Certainly. With a few more discs on the left of the board, that column would score 3 for red. Suppose instead of dropping a red disc into that column, I dropped a yellow disc instead. In that case, the longest line of yellows that would result is 2, either vertically or horizontally to the left. In both those cases, the lines could be extended to a line of 4. Indeed, with the horizontal line, all it would take would be another yellow disc in the column directly to the right of the question mark to win the game. Not that red would ever let that happen, of course. The simple scoring algorithm works like this. It looks at the first empty position in each column in turn, and for each of them, it assesses a series of 4 cells, each in one of the 4 different directions, working out a score for the human player and one for the computer. If a disc of that colour were to be dropped into that space. That all sounds a bit meaningless, so I better explain it using this general example. Here's a column from the centre of the grid, and we're scoring the position marked with an X. Suppose we were to drop a red disk into that position. Like that. Now we're going to score that position from the point of view of the red player. Consider the 4 positions looped in blue. The algorithm asks, could these positions possibly form a line of 4 disks of the same colour, either colour, in the future? If the answer is no, then the algorithm needn't consider those 4 positions at all. They cannot form a line of 4 regardless of what disks fill them in the future. However, in this case, it is possible that those 4 positions could all hold red disks. The algorithm then asks, how many of those positions are currently occupied by red disks? Just one so far, the disk we've just dropped in. That scores 1 for red. Of course, in the game itself, this would either be +1 if the computer were playing red, or -1 if the human were playing red. Similarly, if the 4 positions shown contained 2 red disks, that would score 3, or -3 points. 3 red disks and 1 empty space would score + or -10 points. And the winning line of 4 red disks scores 1,000, or -1,000 if the human is playing red, points. These figures I've just plucked out of thin air, but as you can see, I've heavily weighted the scoring for lines that are closer to being the winning score of 4 in a row. Then the algorithm checks the 4 spaces just to the right of the previous set, also including the current space. From what you can see on the screen, that would score 1 point for red. The next horizontal position scores nothing. This is because it is impossible for this configuration to contain 4 disks of the same colour at any point in this game. And the same for the final horizontal position. After that, the algorithm checks the positions along the southwest to northeast diagonal in a similar manner. The one position along that diagonal that it doesn't check is this one, as it will contain an invalid position. The algorithm then checks the positions vertically below the current one and all suitable positions along the other diagonal as well. All these figures, positive for the computer and negative for the human, are added together to give a final score for this potential board position. Here's the code that does all this scoring. In explaining it, I'll work from the bottom up. The function score4 takes 4 board positions and a number representing one of the 2 players and returns a score for them. It doesn't know or care whether those 4 positions are horizontal, vertical or diagonal, or indeed where they are on the board. It simply counts how many of them correspond to the player and returns a suitable score. The disks for the human are represented by the number -1 in the grid, and those of the computer by +1, in keeping with the fact that scores should be negative for the human and positive for the computer. The function Scorquartet takes 4 spaces on the grid, again without worrying exactly where they are, and scores them for both the computer and human, returning the result as a single number, by calling the previous function twice, once for the computer and once for the human. Note that if both the counts for the computer and the humans are bigger than 0, then the score for that position has to be 0. This corresponds to a group of 4 cells with disks of both colours, and which cannot form a winning position for either player at any point in the game. Now I have to take a slight detour, so that what comes afterwards makes sense. The board position, representing the current state of play, is stored in an array of 42 values called current. 6 rows of 7 columns each comes to 42 values. Remember this image? When the computer is choosing its column, it hypothetically drops a disk down each of the 7 columns, and for each of those, it equally hypothetically gets its human opponent to drop a disk down each of the columns in reply. It must therefore consider 7 times 7 equals 49 possibilities. And those possibilities are held in array G. For all positions, all the spaces are set to 0 to indicate empty. They will gradually accumulate -1 values for the human player's disks and +1 values for the computer's disks. I haven't specified how those cells within each board position are arranged in terms of rows and columns. No, we have a function called cell to do that for us. It takes a board which could be one of those stored in G or the current board position, and a row number and a column number, and extracts the value corresponding to that board, row and column by multiplying the row by 7 and adding the column. This means that the disks in the first row are stored in elements 0 to 6, the disks in the second row in elements 7 to 13, etc. I could easily store them the other way round, i.e. down the columns rather than along the rows, but I chose to do it this way. Of course, function cell only returns an existing value in a board. It can't be used to set values to disk colors. That's why you'll be seeing this row number times 7 plus column number quite a lot in the code, as long as the code is consistent. Note that the code automatically filters out any attempt to access a board position which is off the grid. The row numbers range from 0 to 5, the column numbers from 0 to 6, and any attempt to access an array element outside those ranges returns a dummy value of -9999. In scoring board positions, there's no way that this could be confused with an empty space or a disk of either colour. This is useful as it means we don't have to check repeatedly that numbers are within range. The function Scoreboard, of which a few lines are shown here, is a very large one. It takes a particular board position in G and scores it on all the possible groups of the 4 cells that you saw looped in blue a few screens back, horizontally, vertically and along both diagonals. All these figures are combined in one final figure called score, which is set to 0 at the start of the function. What you are looking at is the lines of code that score the horizontal loops going through the position of interest, which is on row R and column C. The computer's dropped a pretend disk in a particular column, got the human to drop an equally pretend disk in a column in reply, not necessarily the same column, and the position of that human disk is the position that we are considering. Cast your mind back to that example board position that you saw. Nah, what the heck. You don't have to cast your mind back. I'll stick it up on the screen. There. You'll remember that there were 4 loops horizontally that have to be considered. That's one. Here are the other 3. Each of those corresponds to one call to function Scorquartet. Of course, these different loops contain several cells in common, and to save computing time, I've stored all the cell positions that are tested more than once in temporary variables, the ones starting with X. Now, I know what you're thinking, mainly because I'm staring at you through your window while you're listening to this. Go on, take a look. See that ugly bloke with his face pressed up against the glass? That's me. You're thinking, hang on. If we're testing board configurations where we know that at least one cell contains a human player's disk, why is the function testing for a computer score as well? And you're right, of course. Function Scorquartet carries out a test from both the computer's point of view and the human's point of view. All the board positions tested are ones where the human has just dropped a disk, so half this work is wasted. However, remember I create these programs in the forlorn hope that somebody watching them will take them and polish them into something worth running. In this case, you might well aim to add an extra layer onto the game tree, meaning that you'll be testing the computer's response to the human's response to the computer's potential move, in which case you'll need the call involving the computer's disks. However you want to code it, at some point you'll want to streamline proceedings by simplifying function Scorquartet and the lower functions it calls. Remember, the computer's response time is all important in this game. Nobody's going to want to play against a machine that takes a quarter of an hour to play its move. I should also point out it's necessary to calculate computers' moves as well as human moves for the purpose of discovering whether a line of 4 is still possible for any position. If it contains so much as one computer disk, the human being cannot get a line of 4 there, so you'll need to calculate it for that. Of course, the only lines I've given here are the ones where it tests the horizontal position. Similar code to this is required to test vertical and diagonally. I'll only mention one other function before I finish, and that's the function FirstEmptyRow. Every time the computer tries to drop a disk, either while cogitating or for real, or the human drops a disk, the code must determine where the lowest empty space in the column is. Disks drop as far as they can before stopping. This function is therefore called a lot. The function takes a board from G or the current board and a column number. It either returns -1 if the column in question is already full, or counts down from the top row, row 5, to the base, row 0, until it finds an occupied space. If the row is empty, it returns 0, indicating that the first empty space is on row 0. Otherwise, it returns the row just above the first disk it comes across. And there you have it. I have not mentioned the function computer response, which is called automatically when the human makes his choice, and which ties everything you've seen above together. Nor have I mentioned minor functions, like the one needed for the human to choose in the first place, or the function needed to detect if one player has won. It's been an unusually sketchy description of the program, but I have 2 reasons for that. Firstly, I'm well aware that this video is already longer than the others on this channel. In fact, I can see your eyes double glazing over right now. Remember, I'm looking at you. Secondly, I'm not at all happy with this code, particularly the scoring algorithm. As it stands, it is actually possible for the computer to miss a winning move simply because it's only judging human responses to moves. It's as though it's looking at the human response on the far horizon and the winning move is right under its own nose. Of course, if the computer played the winning move, the game would end, but the Minimax procedure, as I have implemented it, doesn't take that into account. It assumes that the human would respond to that winning move with another disk, and judge the ball position based on that. That's a glaring problem that needs to be fixed. If you try running the code in its current form, you'll find it plays an utterly lousy game of Connect 4. All in all, I can see that this is code which is going to need a great deal of tinkering with to get something even vaguely worth running. And that's what I shall be doing if I have a few spare moments in the near future. Don't be surprised if the code you see on my website, link below of course, differs slightly from what you see here. However, I shall keep the same basic structure of the program, so it shouldn't differ too much. So, to anyone watching this video who fancies the task, please do take this particular sow's ear and turn it into a silk purse. And do let me know the results, of course. It will be most interesting to hear how you've got on. Until the next time, thank you for watching and goodbye.